Welcome to Understand Chemistry. I am Dr. Bilal. In this video, I will discuss experimental determination of copolymerization parameter R1 and R2. At first, let us take a closer look at the Mayo-Lewis method for determining copolymerization parameters. For this, we begin with the Mayo-Lewis equation. This equation relates the mole fraction of monomers in the copolymer represented by small m1 and m2 to their concentration in the feed given by capital M1 and M2 and the reactivity ratios R1 and R2. Here, R1 and R2 are called copolymerization parameter and are defined as the ratio of the rate constants, specifically self-propagation over cross-propagation. So, R1 is equal to K11 over K12 and R2 is equal to K22 over K21. This gives us a mechanistic insight into how each monomer prefers to react either with itself or with the other monomer. Now, in order to find the reactivity ratio using Mayo-Lewis method, we solve Mayo-Lewis equation for R2. We rearrange the equation. First, we expand and simplify the terms. After a few steps, we arrive at the following equation. To simplify, let us use the notation A and B, where A is equal to ratio of capital M1 over M2 and B is equal to small m2 over small m1, and the final expression becomes R2 is equal to A square BR1 plus AB minus A. This final expression allows us to calculate R2 using known monomer concentration and experimentally determined copolymer compositions. However, since both R1 and R2 are unknown, we need at least two sets of data to solve the system. The second set of data is obtained ideally from experiments with different monomer feeds, capital M1 and capital M2, and determine small m1 and m2. Once we have multiple dataset, we plot them using the equation R2 as a function of R1. We obtain a separate line for each experiment. The point where these lines intersect represents the estimated value of the copolymerization parameters R1 and R2. As mentioned earlier, at least two datasets are required to solve the system of equations. However, incorporating more dataset from additional experiment enhances the accuracy and reliability of the results. For example, in this plot, we have 4 lines derived from 4 different datasets, which helps us narrowing down the intersection region and improve confidence in the parameter estimation. Now let us move on the Finemann and Ross method, which offers determination of reactivity parameter from gradient and intercept of straight line using Finemann and Ross copolymerization equation. To derive Finemann and Ross copolymerization equation, let us start with the mole fraction form of Mayo-Lewis equation. In my previous video, I have shown you how we reach to this equation. Here F1 and F2 are the mole fraction of monomers in the copolymer, while small f1 and small f2 are the mole fraction in the feed. To simplify the equation, we eliminate F2 by substituting F2 is equal to 1 minus F1. This leads to a series of simplification steps that isolate F1 as shown here. Now let us solve this equation by separating R1, R2 containing terms and all other terms in order to reach an equation of straight line. After solving the equation for R2, we reach to this equation. For sake of simplicity, let us substitute x and y in place of big fractions. By doing this, we reach to the equation of straight line where R1 is gradient or slope of the line, while copolymerization parameter R2 is correspond to the intercept. This line can be plotted as shown in this figure. So in sum, if we want to find a reactivity parameter. Using Finemann and Ross method, we perform series of experiments with different values of mole fraction of monomer M1 in initial monomer mixture. For each experiment, we obtain a set of x and y. The data is when plotted give us a straight line, the slope or gradient of which is equal to copolymerization parameter R1, whereas the intercepts give us value of copolymerization parameter R2. Hope you understand how reactivity parameters are determined experimentally. If you have any question, please write in the comment box. Thanks for watching.